Thank you. Thank you so much for joining John Niroula's PhD defense, even though it's getting fairly early in the day, and I know many of you are ready to go to Professor De Laramo's exam later in the day. So it's great to see you all here. It's really amazing to be able to introduce today's PhD defense. I am very proud of what John has done over all these years. When I think of John, I immediately think of my group. I mean, he has been such an important part of everything we've done in the group for all these years. He started as a PhD, as a Europe student many years ago, working on graphene for a month. He ran away from me as soon as he could. Then we overlapped briefly in 6012. Then he decided to pursue his MH degree in the 6A program that I was directing at the time. And finally, I convinced him to stay in the group for a bit longer for his PhD. I had to promise him he would not touch graphene in any way or form. But he has been doing amazing work on high temperature electronics since then. He has been really key for the gallium nitride part of the group. If you talk to one of my students working on gallium nitride and you ask him or her, hey, do you think we can do this project or that, or what do you think about collaborating with this company? They won't say, oh, let me check with Tomas. They will say, okay, let me check with John to see what he thinks. I feel like I would have not been able to have that we have if it wasn't because of John. So John, thank you so much for everything you've done for the group. Thank you so much for everything you've done for the lab, for MTL, and I was very much looking forward to your PhD defense today.
Thank you so much for coming to my PhD defense. Yeah, I'll talk about thermally hardened RF GaN MEMS in extreme environments. And I just want to take a minute to thank MTL, MIT Nano, MIT ECS for all the years I've been here and all the wonderful work and how and the support they've done for me. I'll also take a little bit of time and acknowledge our funding sources, namely NASA, Lockheed Martin, the Air Force Office of Research for the projects, as well as internal funding from, or sorry, fellowship funding from NDSED and the Qualcomm Innovation Fellowship. So the outline for my talk today is kind of focusing on these 5 research questions, or 4 research questions, mainly motivation on why we should care about high temperature electronics at all, and specifically gallium nitride in that space. What are the high temperature properties or electronic properties of AlGaN-GaN heterostructures? We can understand them and then design better devices. And how do we go about making high performance transistors? And then how do we go about modeling these? And then I'll end with a very quick summary of key contributions and a little bit on future work. All right, so we can get started. So why should you care about high temperature electronics? One, it looks cool, but as you probably know, modern electronics has really changed our lives for the better. Everything nowadays is with your phone, with the internet. It's hard to imagine not being able to use those. And it's been 50 years, and there's still so much more applications for electronics to come. I think that's some really important ones that are coming up in high temperature electronics. And I'll list a few of them here. Specifically, there's a lot of exciting work on geothermal energy, being able to extract energy directly from the earth. It's one of the most renewable ways to extract energy that we know of. The hard part is that you have to dig all the way down to the earth and reach rocks that are at 400, 500 degrees Celsius. And it's not possible with current mechanical system as well as electronics. And so we need electronics that can survive and be able to operate equipment at those temperatures down there. Additionally, there's been a lot of recent interest in hypersonic vehicles and defense systems. These hypersonic aircraft travel at like 5 or 6 times the speed of sound. And so they get so hot that the outside of the wings get to about 1,000 Celsius or so. And even with their insulation, the insides get to 400 or 500 Celsius. And you can't just add more insulation because it'll make the aircraft much heavier. There's also a lot of exciting space applications, specifically the surface of Venus is at around 500 Celsius or so. It's the main reason why we can't send rovers to Venus. We send rovers to Mars every year, but there's nothing that can send to Venus that can move around on the surface of Venus, mostly because the electronics just won't survive more than a few hours there. Additionally, there's a lot of industrial applications, mostly in aerospace, automotive, and chemical industry, sensing and monitoring hot exhaust or hot chemicals, and feedback and relaying that information to a centralized system to add intelligence, add feedback, add efficiency to these very important critical processes. Turns out silicon just can't provide the solutions we need at these high temperatures. And that's almost at a fundamental level. Most silicon devices operate on this idea of a p-n junction. However, that starts to fail once the intrinsic carrier concentration or the background level of the silicon or semiconductor gets to really high temperature, because this intrinsic carrier concentration increases exponentially with temperature, as you can kind of see in this black line here. And for silicon around 200, 250 Celsius, you start getting into the 10 to the 15 range, which is around the range of typical dopants. And so all your p-n junctions end up just as kind of resistors. And so you can't make a rectifying junction, you can't make a switch, you can't make a transistor. But lucky for us, this intrinsic or background carrier concentration is also an exponential function of the band gap. And so that's where wide band gap semiconductors like silicon carbide or gallium nitride come in, and we can operate at least theoretically up to 1,000 Celsius. And we see this in practice too. If you try to buy a silicon or a SOI technology, it's almost always rated to at most 250 Celsius. So we need a wide bandgap material. There's been a lot of work already by silicon carbide. Silicon carbide is kind of like the older brother of GaN. It's been around for about 20 years more than GaN. And the folks over, especially at NASA, have really pioneered some really amazing work at high temperature silicon carbide electronics. And they're currently at the level where they can demonstrate about like a small little RAM cell with about 1,000 transistors operating at 500 C. But we think we can do much better with gallium nitride. And this is kind of from once again, a fundamental point of view. To begin with, even at room temperature, GaN has much better material properties than silicon carbide. If you look at things like the mobility, the saturation velocity, the critical field, which are really important device or material level parameters, GaN always has a much higher version of that compared to silicon carbide. And this translates to about 4 to 5 X in a lot of figures of merit at room temperature. And a lot of this continues at high temperatures too. If you look at, for instance, the Hall mobility versus temperature for silicon carbide devices, as you can see in black here, and algan GaN devices, as you see in blue here, you can kind of see like the algan ones are always higher, even across the whole temperature range. And if you extrapolate to kind of 500 Celsius, the algan GaN devices typically have a Hall mobility of about 200 centimeters per millisecond, while the silicon carbide devices have about 20 to 80 at most. And once again, this is the Hall mobility, not the field effect mobility, which for silicon carbide devices can be considerably lower. And we see this in practice too. There's been previous work in our groups, specifically like from Dr. Ming Yuan. on demonstrating that you can make a GaN ring oscillator and operate at 500 C. And you can get about an order of magnitude improvement from kind of an equivalent silicon carbide ring oscillator. That being said, these devices that were made here were relatively slow in the grand scheme of things. They were fairly long channels. And so their frequency range were kind of in the 100 megahertz range. But for anyone who works on GaN, you know that's really slow for GaN. GaN can operate in the hundreds of gigahertz range at room temperature at least. And so that's been kind of the motivation for this thesis. Can we get thermally hardened high temperature GaN devices that have an RF-like device structure so that we can get ideally a gigahertz operation at 500 Celsius and above? Okay, so I'm gonna take a quick aside. There's gonna be two types of measurements I talk about in this presentation. For the most part, there's one type is the short duration or hot chuck measurements. This is kind of what most people think of when you do a high temperature measurement. You put your sample on a chuck, raise it to that temperature, so your device is at the temperature of the chuck, and then you do all your electrical measurements that way. Usually this is in air, and usually takes over about several hours, maybe 5 to 6 hours in total, 1 hour at each temperature or so. The other type of measurement are what I'll call kind of long duration furnace measurements. Here we're putting our devices in an oven, annealing them basically at 500 C for several hours or for several days, and then measuring those devices at room temperature to understand the degradation and how the devices change over time. So I'll try to emphasize each time, but just so you're aware. Okay. All right, so now we can go on to kind of the first research question that we have is, what do the properties of these devices or the algae GaN heterostructure specifically look like at higher temperatures? To begin with, I'll start with a very basic algae GaN structure. Algae GaN structure has a little bit of gallium nitride, and we grow some aluminum gallium nitride on top. And because of the polarization difference between these two materials, it turns out that you get a really nice electron or a 2D electron gas, which is a sheet of electrons that's really conducting that you can flow between two ohmic metal contacts and also modulate. And that's really the heart of our device. And most of the properties we care about are associated with this 2D electron gas. If you ask a device person, there's kind of like 4 or 5 parameters that are really important. And most people, if you tell them these parameters, they'll kind of know if your transistor will be good or bad. Some of them include the 2D electron gas density, how many electrons you have in there, the mobility, like the low field transport, the drift velocity, specifically kind of in the higher field transport region, as well as the contact resistance associated with the metal contact to this 2D electron gas channel. Additionally, you can have regrown contacts here, which are relatively better performance, or a little bit more standard is you can have alloy contacts where you deposit your metal, in this case, titanium aluminum gold, and then you alloy it so that you can make ohmic contact to your 2D electron gas. And by making these kind of resistor or TLN detectors, we can vary these length here and we can extract some of the sheet resistance and the contact resistance values, which I'll show in the next few slides. Additionally, we can also make structures that are just heavily doped GaN, and this helps us compartmentalize and extract some of the resistance components associated with the contacts. We can also make some Hall structures, and from this we can actually measure the density and the mobility directly, and we can do that as a function of temperature. So all of this in total allows us to basically measure a lot of these important parameters, namely the 2D density, the mobility, the drift velocity, and the contact resistance as a function of temperature, and understand what's limiting our device performance. Okay, so that's what we did. We did some TLM measurements where we measured those resistors for various different lengths. And from the slope, we can get the sheet resistance. From the y-intercept, we can get the contact resistance. We can see that as we increase the temperature from 25 C here to 500 C, the slope increases dramatically, while the y-intercept, namely the contact resistance, doesn't change too much. And we did this for n equals 4 sets of samples to have some kind of statistically significant amount of data. And the error bars here represent 95% confidence intervals. And we can do this for the regrown sample with regrown contacts as well as alloy contacts, and they more or less look pretty much the same. We can actually plot the sheet resistance versus temperature for these two samples and see that at room temperature, the sheet resistance is about 350 ohms per square, and at 500 C, it increases about 10x to about 4,000 kilo ohms per square. Interestingly enough, if we ramp that, and this is due to what I'll show you later, is due to photon scattering. which has a very strong temperature dependence. Interestingly enough, if we ramp the temperature back down and cool the device and remeasure, we can see that the remeasured points after cooling down are pretty much identical to the points before heating it up. So there's very little device degradation, at least for short-term measurements over the course of a few hours up to 5 degrees Celsius. Interestingly enough, we can also measure these highly doped GaN structures here instead of the 2D electron gas structures. And we can see that that sheet resistance as a function of temperature does not change much at all. And that's mostly because it's limited by ionized impurity scattering or dopant scattering, which has a relatively weak temperature dependence compared to phonon scattering we see in the 2D electron gas. Okay. And more importantly, from that liner set, we can actually extract the contact resistance as a function of temperature for both the regrown structures as well as the alloy structures. And we can see that in general, there's not a whole lot of change over the full temperature range, definitely not that 10x we see in the sheet resistance. And for the most part, the error bars get really large as we increase the temperature, mostly because the sheet resistance gets very high, and so it becomes difficult to extract that y-intercept. Additionally, for the regrown structures, we can actually use those highly doped structures we had measured before, and we can deconvolve the contributions of the contact resistance to RC1, the metal to N++ GaN resistance, RC2, the N++ GaN resistance, and RC3, the N++ GaN to 2-day resistance. And because the sheet resistance of the N++ GaN is very low and very constant over temperature, we can actually get very small error bars for RC1 and RC2, as you can see in these red and green circles here. But for RC3, which is the interfacial resistance associated with the contact to the 2D electron gas, that has very large error bars, once again, because it gets difficult to measure because the sheet resistance of the 2-day is at these temperatures. And so the error bars get quite large. We can benchmark some of this work to put it in context to other works in the literature. You can see our work here in red and literature works in blue of the normalized contact resistance, so RC normalized to the room temperature value. You can see pretty much everyone, there's a lot of work at about 200 to 300 Celsius and less, mostly because that's typical temperature on most probe stations. That's a typical temperature you have to go for reliability measurements. But there's not much work going beyond that. So that's what we're kind of doing here. And you can really clearly see here where the error bars significantly increase as you go to higher temperatures. Similarly, if you look at the sheet resistance, once again, you can see there's a lot of data points at 300 C and below. And this trend is the same to ours, but there's not a whole lot beyond that. And so we're trying to understand what's going on with these related temperatures. And you can once again see here, the sheet resistance significantly increases as a function of temperature. And up to 500 C, it's about 10 to 15 times higher than it is at room temperature. And so we want to understand what is causing this really high sheet resistance. And to do that, we can actually look at some of the Hall structures we made, which are very similar in structure to the TLM resistor structures, except they're just much bigger, 10 millimeters instead of 10 microns, for instance. And that's just mostly due to the measurement system of the Hall. Hall measurement system requires samples that are on this size. So we can do Hall measurements of these structures as a function of temperature for the same type of capital structure. And we can see that the 2-day density up to about 400 C doesn't really change much from 9E12 to 8E12. So that's about a 15% reduction. On the other hand, if we look at the mobility, which is this dashed line here, it goes from about 2000 to about 250. And so that's a 7x reduction. So the mobility decreases by 7 times, or 700%, while the 2-day density decreases by about 15%. And the sheet resistance is inversely proportional to the product of these two. And so we can safely say that the large sheet resistance we see is due to the mobility degradation. And this is kind of in line with other works. Once again, there's not a whole lot of other works at higher temperatures, but the few ones that are, there's about 3, are shown here in blue. And you can see the normalized 2-day density to the room temperature 2-day density generally doesn't change more than about 15% plus or minus across a full temperature range up to 500 Celsius. On the other hand, the mobility in our work and the other works in the literature degrades significantly, and it goes from 1 to about 0.1 or 10x at 500 C. However, it's interestingly enough, it's quite a different story in the high field transport case. Typically, the mobility is a low field transport parameter. And so we can actually try to understand what's going on in the high field. Since we have these TLM structures or these resistor structures, we can break down the resistance components. It's basically 3 resistors in series, 2 in the contacts, and then the resistance in the channel.
we can take into account the IR drop of the contacts. Because we know the contact resistance, we measure that as a function of temperature. And so we can actually get the voltage drop across the channel. And we can calculate kind of an average electric field across the channel since we know the length of this TLM structure. Additionally, we know that we can measure the current of the TLM structure. And since we know the 2D density from the Hall measurements, we can actually get the average drift velocity in the channel. And so that's what we do. Using these formulas, we can convert kind of standard current voltage measurements of this TLM structure from 25C to 500C. And we can convert it to basically drift velocity versus electric field measurements, which are a little bit more physically insightful. And from here, you can actually see two interesting things. One is that indeed in the low field limit, where the mobility is kind of the main parameter, there is indeed a 10x drop as you in the drift velocity. However, in the high field limit, you can kind of see that the drift velocity doesn't change too much, about a 1.7x drop from 25C to 500 Celsius. And so we can see that the high field transport reduces much slower with temperature than the low field transport does. And so that gives us some idea of how we want to design our devices in general. All right, and surprisingly, this is actually not super new in the sense that people see this in gallium arsenide, a little bit older semiconductor, but in kind of the opposite direction. Gallium arsenide has a really low band gap, so you can't really use it at high temperatures, but you can measure it at very low temperatures. And so if you look at kind of the drift velocity versus electric field, this is the log scale of it now. From 4 Kelvin to 77 Kelvin, you can see in the low field limit, the drift velocity doesn't decrease by a factor of 10. But in the high field limit, they're very close to each other. And so you kind of see the same phenomenon occurring. And ultimately, this is because of the different phonon scattering mechanisms. In both cases, phonon scattering is what's causing the decrease in the drift velocity. But in the low field case, it's more phonon absorption. The electrons need to basically meet a phonon, absorb a phonon, and scatter across a phonon. And so it depends on the number of phonons, which is very dependent on the temperature. On the other hand, in the high field case, it's more of a phonon emission process. So the electron doesn't have to wait around to see a phonon. It can just emit a phonon directly. And so that has a very weak temperature dependence. All right. In addition to kind of doing those hot chuck measurements, we also put these samples as same samples, although virgin samples, so they haven't been measured. We put them in a furnace, measured, annealed them for around 8 hours or 24 hours, and measured them at room temperature repeatedly. And so we can actually measure the contact resistance versus time for devices annealed at 500 Celsius. Once again, these are all measured at room temperature. So we can see something interesting. We can see that at around 48 hours or so, both the sheet resistance and the contact resistance starts to dramatically increase, and the error bars get very high as well. And so it's stable up to then, but it starts to degrade afterwards. So we wanted to understand what is going on here. From that, we actually did a few microscopy studies where we looked at TM images of pristine samples and samples that have been through the full 72-hour 500C exposure process. The TM images here are different mostly because the tools are different, but we can see that both in real space and in case space, the crystal quality is basically perfect. We can't see any cracks or dislocations that have been formed due to this 500C anneal, at least for the regrown contact structures. Similarly, we can look at the alloy contact structures, and we can look at pristine samples and samples that have been through the full 72-hour exposure. And we can see that at least structurally, there doesn't seem to be any change. Additionally, if we look at the elemental composition through EDX, we can see there is indeed tile nickel gold that has been alloyed altogether. And that hasn't significantly changed as we have annealed the sample. And so we suspect that the contacts themselves are perfectly fine. But what is going on is the sheet resistance is indeed changing. And so we suspect that we did some AFM measurements of a pristine sample. And the same sample, we looked at the same area after the high temperature exposure. And you can kind of see here that the surface morphology has significantly changed after the full high temperature exposure. The roughness has increased from 1 nanometer to 2.2 nanometers, and the topology has significantly changed. And so it's not really a contact issue, but it's a fact that the algan barrier is degrading, and that's making the contact measurement very difficult. Surprisingly, we can also do kind of the same experiments in air instead of the nitrogen environment, as was in the previous slides. And we can also try passivating the sample with a few dielectric layers. So we did that. Surprisingly, unpassivated samples in air can actually last up to in this case, 150 hours without with very little degradation, maybe 50%, not the 5x we saw in the nitrogen environment. Similarly, if we cap the samples with 50 nanometers of silicon nitride or silicon dioxide, or 100 nanometers of silicon nitride, silicon dioxide, those samples can survive up to 216 hours or roughly 9 days. The reason for this, we suspect, is basically in air, there is an equivalent passivation layer because the sample gets oxidized. However, in an inert environment, the sample is not passivated. And so there's a lot of surface states, a lot of dangling bonds, and we suspect that cracks are forming in those bumps you saw in the AFM are forming from those surface states. And that's what's leading to the degradation. And so we find that if we make these devices and they degrade much slower in air than in an inert environment, which is often kind of which is kind of the opposite of what you'd expect for a typical chemistry experiment. All right, so just to sum up this portion here, what did we learn about high temperature properties of alkane heterostructures? We learned that the 2-dig density and the RC are roughly constant up to 500 C. We've learned that the mobility decreases a lot, 10x, but the high field drift velocity maybe around 2x or so. We've learned that the contacts seem pretty solid, at least without bias, and over a 72-hour period at 500 Celsius. And we've learned that it's actually, the structure is more stable in air than in nitrogen, mostly because of the surface degradation. It happens worse in nitrogen environments. So armed with that knowledge, now we can start to understand how we can make a really high-performing HEMT or transistor at these high temperatures. What we did first is we used some of the technology that previous grad students had developed, which are these p-GaN gated alkane GaN HEMTs, where they use a tungsten refractory metal and halogen nickel gold contacts. These devices were luckily had the chance to be tested in a Venus environment over at NASA. And basically they have this big chamber here, which is roughly the size of a person, and they flow a lot of toxic gases like nitrogen, carbon dioxide, sulfuric dioxide at 465 Celsius at 92 atmosphere, which is to simulate kind of an Venus environment. And we did that for 11 days and measured these devices basically every hour continuously in these conditions. We found that the devices work pretty well. For instance, you can see here the initial measurements at the start of that 465 temperature and the final measurements. There's maybe about a 20% decrease at most. Additionally, if you look at the transfer characteristics, namely the drain current and the gate current, before in black and final in blue, you can see they lie more or less right on top of each other. And because we're measuring and so there's very little degradation over the full 11-day period, and we can track this a little bit more carefully since we've been measuring the devices continuously every hour for the full 10 days. We can see that things like the drain current, the gate current, and the threshold voltage really have changed maybe at most 20% over the full period, which is quite surprising and quite good for being able to make something that can last in Venus, at least for a while. So from this p-GaN gate structure, we can actually find that it operated great in Venus. However, there's kind of two key issues with this device structure moving forward. One is that this p-GaN right here is really thick, it's 70 nanometers. And so if we want to scale the device dimensions to be able to reduce short channel effects, we want to be able to not have this p-GaN layer here because it's 90 nanometers. And so we need to be able to shorten the gate length to be able to push the frequency performance. And as we saw earlier, it's much better to have a scaled device where your velocity limited than when you're mobility limited. Which brings us to the second point here. If we look at the drain current of this device from 25 C to 500 C for gate voltage of 5 volts, you can see that at 25 C it's about 200 milliamps per millimeter. But as you go to 500 C, it gets to about 20 milliamps per millimeter. And so you see a full 10x reduction, once again, due to that mobility. And so there's a huge drop in the current density because it's a long channel device, because of its mobility limitations. And this is just to put the nail in the coffin. If we look at the field effect mobility extracted from the transistor compared to Hall measurements or TLM measurements, assuming a constant 2-dig density, we can see that they overlap very well, indicating that the transistor field effect mobility degradation is from the same phonon scattering mechanisms we see in Hall structures. All right, so the solution there is we don't want to be mobility limited. We want to make a very scaled device. So what we did is we started off with relatively standard Schottky HEMTs, where they use a nickel gold gate, nickel gold T gate, as well as highly nickel alloy contacts. And this is a 24 nanometer diameter and 25% barrier. And we made a very scaled version of that. In this case here, the gate length was 120 nanometers, and the source resistance was 575 nanometers. And here's the source, drain, and gate right here. And so using this scaled device, we can then see that the RF performance at room temperature is really good. Its FTs are around 95 gigahertz, Fmaxes are around 172 gigahertz. So truly a 100 gigahertz device at room temperature. And we wanted to understand how the DC characteristics of the device are going to change as a function of temperature. That's what we did. We measured the output characteristics at 25C, 300C, and 500C. And you can indeed see that the current density doesn't drop by 10x. It drops by about that 1.7x before, from about 1.5 amps per millimeter to just a little bit under an amp per millimeter. Similarly, if we cool down the device and bring it back down to 25C, you can see that there is a little bit of change, but overall the maximum current and the on-on resistance haven't changed much. And mostly the change I'll show you in the next few slides is due to the shift of the threshold. And we can actually benchmark these devices. We can look at the maximum current density as a function of temperature for all wide bandgap semiconductor devices in the literature for GaN and silicon carbide. And we can see that because we have a very scaled device, we can get very high current densities compared to other GaN devices in the literature that have gate lengths of several microns, and especially over silicon carbide devices in the literature, which currently are about 100x lower current densities than what we are able to achieve. Perfect. So we can see that indeed device scaling really does improve back temperature performance. Similarly, we can look at the transfer characteristics. This is a little bit convoluted here, but the solid lines are the drain current, and the dashed lines here are the gate current. And we can see as you go from 25C to 500C, there's a positive shift in the threshold voltage, and the leakage on the offstate leakage, namely the gate current, increases also as we go to 500 Celsius. Similarly, if we cool down the device, we can see that there's a permanent change in threshold voltage, where now it used to be this blue here at 25C, and now after cooling, the threshold voltage has changed significantly in the positive direction. And we can benchmark this on-off ratio, as many people do, for high temperature devices. And we can see that indeed we're able to get a relatively good on-off ratio across a wide temperature range, and better than a lot of the current GaN devices, and getting very close to the state-of-the-art silicon carbide devices made by NASA. Note this one right here is a HEMT that has 100 nanometers of aluminum oxide. So it's a little bit of an outlier to have a really low off current. However, we noticed that nickel gold is not the ideal high temperature material. As you saw, there was that permanent significant shift in the threshold voltage. And so people over at the AFRL have actually studied this a little bit and saw that if you get some nickel gold T-gate HEMTs and you start annealing them at 400 or 500 Celsius, the nickel layer right here, which is the Schottky contact, actually disappears. It intermixes with the gold, and both of them together start to really diffuse into the allogen barrier. And so that is going to affect your reliability. That's going to permanently change your device. And so most likely for very high temperature applications, it's probably not a viable solution. Maybe you can get away with it at 500 Celsius, but beyond that, it's going to be difficult. So that's what we wanted to do. We wanted to replace nickel and develop a high temperature robust Schottky contact. So what we did is we looked at the periodic table, and here's a periodic table with a list of the work functions, which is an important parameter for determining a good Schottky barrier contact. You can kind of see here that ideally we want to use a really high temperature robust material. Usually that means refractory metals that are correspond to these elements right here. Refractory metals are typically the metals that people use in really extreme environments, typically things like nuclear power plants or jet engine turbines. They're really robust and have really high temperature melting points. However, we want to use nickel because it has a relatively high work function of about 5 electron volts. And so kind of the natural conclusion here is we focus on rhodium, which has the highest work function out of the kind of standard definition of refractory metals. And so that's what we did. We started to develop a rhodium process, but developing transistor technology with refractory metals for the gate is very difficult. It's very difficult to do a lift-off process because the temperatures typically needed to evaporate these materials will often burn or resist, especially things like PMMA, for instance. And so we had to develop an etch back process where we etch a via, sputter the rhodium. And so to do that, we needed to develop an etch top layer to have a robust process. So that's what we did. We developed this ALD aluminum oxynitride layer. The nice thing about this layer is that it has really good selectivity to SiO2. So in the red, it's if you don't anneal it, it has a selectivity of about 7 in fluorine plasma, and it has a selectivity of about 20 in HF or BOE. And then if you anneal it at, for instance, 825 Celsius for like a minute, you can actually increase the selectivity to about 50, which is really good for an etch top layer, and that's what we needed. And additionally, the nice thing about this film is it also acts as a passivation layer. If you look at devices that have this sample with have no passivation and have devices that have passivation, you can see that the material density increases about 30%, and that increase is sustained up to high temperatures, 400 Celsius. While the mobility, which is in this dash right here, it's a little hard to see, but they're right on top of each other, so the mobility doesn't really increase at all. Right. Additionally, we wanted to make sure that this film is actually insulating at high temperatures. So we made some tungsten aluminum oxide min capacitors, and we measured the current and voltage characteristics. In this case, normalized current to the area and the electric field normalized to the thickness of the film from 25 Celsius to 500 Celsius. And we can see that the critical field drops a bit from about 7 to 8 megavolts per centimeter to 4 megavolts per centimeter, but it's still a relatively insulating material, and 4 megavolts per centimeter is bigger than the electric field of gallium nitride, and so we're happy with that. You can actually see that the leakage we see here, if you plot it on a log of J/E versus square root of E scale, it increases with temperature, and you get straight lines here, which is indicative of a full Frankel like tunneling mechanism. So that's the main leakage mechanism for these films. All right, so now that we have all that, we can actually start our high temperature refractory gate process. This time we started with AlGaN of 25% and 18 nanometer sticks on a silicon carbide substrate. We did a regrown process this time for the omics. We deposited oxide, etched the oxide in fluorine, etched the GaN in chlorine, and then we can send it to our ME friends at OSU, and they can grow some really nice N++ silicon doped GaN for those foaming contacts. It ends up getting all over the place here, but if we do a little bit of KOH or hot KOH, the GaN on top here is amorphous, and we can remove it very nicely. Subsequently, we can then sputter tungsten all over the sample here, and we can isotropically etch some of the tungsten in peroxide to remove some of these sidewalls here. And then we can actually lift everything off in BOE so that we have basically a self-aligned tungsten refractory omic process. Afterwards, we can deposit our etch stop layer, the ALD aluminum oxynitride, and then we can also deposit pads and do the mesa etch. And from here, we can actually of the sample and how much we actually back. Now this defines the stem of our T-gate. Then we can finally get to the heart of it, which is continuing that radium metal. So we can etch down the SiO2 with fluorine, stop on the aluminum nitride, and then remove the aluminum oxynitride in a little bit of developer, since the aluminum oxynitride etches very quickly in developer, while the AlGaN doesn't. Afterwards, we can deposit the rhenium, and sputter the rhenium, sputter the tungsten, and then we can actually deposit some gold and nickel for kind of low resistivity filling metals. The reason why we wanted gold and nickel here is mostly from a resistivity point of view. It turns out the gate resistance here is a really important parameter for RF devices. And if you look at gold resistivity, it's about, what we measure is 2.6 microohm centimeter. Theoretically, you get about 2.4 microohm centimeter. And all the refractory metals, at least that we can deposit in our clean room, are at least 10 to 20 times higher resistivity. And so, like for instance, moly is about 200 times higher, even though theoretically it should only be 3 times higher. So although gold in practice is not the most refractory, but it's very good at being a very low resistivity metal. And we find that it works at 500 CLEs. All right, when we've checked this stack here, we deposit the same exact gate stack on an AlGaN GaN structure and just annealed it at in 1 hour at 500 C in air. And we can see that indeed nickel, and we can do elemental mapping here of the nickel, gold, tungsten, radium, aluminum, gallium nitride. And we can see that there doesn't seem to be any obvious diffusion of the nickel into the rhenium and the tungsten layers. Maybe there's some nickel in the gold, but due to the limitation of yes, we can't really say much more than that. All right, so then we can continue with this long process and finally use the nickel as an etch mask and etch down the SiO2. We leave about maybe 50 nanometers of SiO2 and then remove it in DOE just to make sure that we don't get too much plasma damage on the aluminum oxynitride layer that we use both as an etch stop as well as a passivation. And so at this point, the devices are complete. They look something like this, where you can kind of see the tungsten omics, the T-gate nickel gold, and if you squint really hard, you can see the radium layer, radium tungsten there right there. And this is a 200 nanometer gate length. If you do a stem in this region, you can actually see that the radium looks really good. It's actually single crystalline to the algan due to the sputtering process, and the tungsten is polycrystalline to the radium. Additionally, if you look at a little bit on the edge here of the gate, you can actually see that the etch stop layer actually worked, where we're able to see that the radium has this little curvature here, and the aluminum oxynitride also has a curvature here from the fact that the developer was an isotropic etch. We're able to remove that very nicely. Alrighty, so then we made the first ever radium-gated algan HEMTs, measured the frequency performance. For this, in this case, it was a relatively long channel, it's 200 nanometer gate lengths. So the FT was about 38 gigahertz, Fmax was about 72 gigahertz at room temperature. And then we measured the output characteristics as a function of temperature from 25 to 500 C. We can see once again, the current drops not a whole lot, about 2x once again. And then we can do a second round where we cool down the device and then do the exact same thing. And we can see basically more or less the same characteristics we see in the second round, at least from the output point of view, output characteristic point of view. What's interesting is if we look at the transfer characteristics, they change significantly. So in the first round, it's a little bit all over the place. If you plot the drain current versus the gate voltage, the blue one here is 25 C, and then it goes to 100 C in red, and then kind of jumps back to 500 C. You can see that this time the threshold voltage is generally to the left or a negative direction, which is the opposite of what we saw in nickel gold devices. Additionally, if we actually do a second round, we can actually see this time where in this case, all of the transfer curves look more or less identical. The threshold voltage change is very marginal. There is a significant amount of hysteresis, though. That's what kind of this bumps here are, but that we suspect that indeed the medium is working very well at high temperatures. It looks like the nitride passivation is struggling a little bit at very low temperatures, but once you increase the temperature, the detrapping rate is enough that electron trapping is not big, and so you don't get as much hysteresis there. And once again, the gate linkage does increase dramatically as you increase the temperature from 25 C to 5 C. All right, but the second round seems to significantly stabilize the device. All right, and we can benchmark this device against other devices in the literature. Once again, we get very high current densities because of the scaling. And we're able to get a relatively good on-off ratio of about 10 to the 6, which is pretty much identical to what the state-of-the-art silicon carbide devices see at these high temperatures. But once again, we get significantly higher, about 2 to 3 orders higher magnitude current densities. All right, so now we know how to make a high performance, high temperature HEMT. You got to skip, you can get record quote unquote current densities of 0.9 amps per millimeter and 10 to the 4 or 5 on-off ratios for Schottky gates. You really got to scale it to prevent as much low field mobility transport as possible. And then you want to use refractory metals like radium to prevent fusion of the nickel into the alloy. All right, I'll end the very brief slide here with a few slides on modeling these high temperature HEMTs. What we did for modeling these devices was use the MIT Virtual Source Compact Modeling Framework, which basically models kind of almost any GaN transistor using a kind of 3 transistor model of one for the source and drain axis reasons, as well as the interleaved transistor. And it's a charge-based model, and it has a few temperature dependencies, including PSS, the mobility, the threshold voltage, and the saturation. What we did here is we started off with initial guess from these parameters. We've been doing this modeling stuff for a while now, and from a lot of the device level measurements, like the CD, the TL, and the Hall, you can actually get a pretty good guess for a lot of what these parameters should be. And so if you do that and you look at 500 Celsius for, in this case, a long channel device, a 1 micron device, you can see the blue is the experimental data and the red is the model data. And you can look at the output, the transfer, and the gate linkage characteristics. And they're not too far off if you have a pretty good guess. What we can do then, though, is use an automated extraction process using Python and GSpice, where we can optimize various parameters over these curves multiple times So in this case, we can optimize the gate parameters associated with, for instance, the shocking barrier height, the Pohl-Frankel emission, the thermal resistance, the gate capacitance. And we can get a very good fit or match to the gate linkage characteristics, although not as great match to the transfer and output characteristics. Then we can go on to the transfer characteristics, the IDVG characteristics. We can optimize things like the threshold voltage, the sub-threshold slope, the bit hole, and puncture. Once again, we have a pretty good guess for those, but we're doing a full numerical optimization here. We can get a very good match between the transfer characteristics now as well, but still not perfect match in the output characteristics. And then we can do the same thing for the output characteristics. And we can optimize things like the contact resistance, the sheet resistance, the mobility, the injection velocity. And now we can get a really good match in the output characteristics, transfer characteristics, and the gate linkage characteristics at very high temperatures across in a semi-automated fashion. And the most important thing about this is that we can use this thing to really understand the device's form. For instance, we can look at the field effect mobility, the mobility extracted from the transistor characteristics for various device dimensions, in this case, 1 micron gate length and 246 micron source drain distances. And we can do one ramp in solid lines and then another ramp in dashed lines where we ramp the device up to 500 C, pull it back down, and then do another ramp here. You can kind of see the mobility values all lie on top of each other. So we see that there's really no degradation in the field effect mobility of the transistor as we go from one ramp to two ramp. And it's pretty consistent across several different device dimensions. So the field effect mobility, we can conclude, does not change permanently with temperature. However, we can look at things like the shocking barrier height that we extract. And for the same set of devices, we can see that between ramp 1 in dashed lines and ramp 2 in solid lines, there is not only an increase in the shocking barrier height, but a permanent change in the shocking barrier height when we return to room temperature. And similarly, we can look at things like the ideality factor and once again see that at, in the ramp 1 case, it's very large, but in the ramp 2 case, it reduces significantly in a permanent manner, and once again, still decreases as we increase the temperature. And so both the shocking barrier height and the ideality factor have permanent and non-permanent changes, potentially associated with things like trapping, which are non-permanent, and metal diffusion into the gate, which would be permanent. Great. So I'll end now with a summary of some of the key contributions of this thesis. All right, so we've learned a lot about, a good amount about the high temperature properties of alkaline anhydride structures. Main takeaways here are low field transport decreases rapidly with temperature, but the high field transport really doesn't. And devices can survive in air at least for a few hundred hours, 100 hours or so, at least without any bias applied. We can also make demonstrations of really scaled nickel gold and rhenium-based kits with really good RF performance at room temperature and record Imax and on-off ratios at high temperatures. And similarly, we can make an automated modeling parameter routine, which helps us understand permanent versus non-permanent degradation of the device as a function of temperature across various ramps. All right, so future work. One of the main things I wanted to do in this thesis, but didn't get a chance to, would be to do high temperature where we measure at parameters and
Could you plug in my laptop?
Setup of the and so we didn't get a chance to do that here, but over the next few months, we hope to finish that. Additionally, we want to do a little bit more material analysis of the radiant gate before and after the temperature sweeps. Understand, is it oxidizing? Is it stress changing? What is going on with it? And also ideally do some long-term high temperature testing with bias applied, which would be the most relevant use case. In our previous works, we didn't really apply any bias in the many hour long-term testing at high temperatures. We also want to explore new materials potentially in the future. You can actually see here the mobility versus temperature plot of AlGaN. You can also look at it for indium aluminum nitride. And you can see at around 500 Celsius, they actually cross. Although at room temperature, the indium aluminum nitride mobility is half of the AlGaN mobility. And so this makes us think that there are certain materials that have a lower degradation in the mobility as a function of temperature. And they might not be better than AlGaN at room temperature, but they might be better than AlGaN at very high temperatures. And so that's what we want to explore, for instance, indium aluminum nitride or AlGaN channel devices, which may have a higher charge density or a higher mobility at your operating temperature of interest. Last but not least, we want to use some of that MVSG modeling work that we've developed to develop a high temperature RF PDK so that we can actually make an RF transistor, fabricate it, and try to test it and have a high temperature operating unit. All right, this is the publications that I have. I will skip over this quickly. And I'd like to take a few minutes to kind of do a bunch of acknowledgements, if that's all right. First things first, I want to acknowledge my thesis committee. Thank you so much, Professor Del Alamo, Professor Velasquez, Professor Alamo, Professor Lane. I really appreciate all the useful insights you have. I will kind of embarrass you one by one if that's okay. Professor Professor Velasquez, my most memorable story of you actually is I took your 6012 class when I was an undergrad, and it was basically one of the best classes I ever took at MIT. And I had a lot of fun with it. And I remember towards the end of the semester, I was moving out of my dorm. I lived in one of the on-campus dorms at the time, and they have basically, when you move out, they have piles of kind of trash or recycle bins where you can put, books you don't want, clothes you don't want, electronics you don't want, and it gets donated. So for some reason, I decided to check my mailbox because I check my mailbox at the end of the semester, once a semester, and I actually had a physical letter there. And inside the letter was something along the lines, it was from Professor Velasquez. It said something like, oh, John, you did really well in this class. You were in like the top 5%. You should consider this field or something like that. And I was really touched. I was like, wow, I can't believe he actually took the time to do that. And then he's like, here's this book you can read to like motivate you or something. And it was this book here, which is a biography about Bob Noyce. And then I opened the book, and then I read the first page, and I was like, I'm never gonna read this. I don't read books. I was more of a YouTube person. I'm still more of a YouTube person. So I put this book in the unused book pile. I donated it. I was 19, I was very young. I would love to tell you since then I've changed and I've read this book, but that is not true. I ordered this book on Amazon on Friday. I was supposed to have it today, but it didn't arrive. So I will read it before I finish it. Yeah, but just to let you know that those letters really do work. Us students really appreciate your kind words, even if the gifts don't always go. Professor Del Alamo, you were my undergrad advisor. I learned, it was my first experience in semiconductor devices in gas convents with Alon, who was my mentor. I really enjoyed it. It's what made me fall in love with semiconductor devices. I remember with Alon, I was telling him I was considering med school at the time versus semiconductor like electrical engineering. And based on my interactions with him and just like our conversations, I really loved what we did. And so I ended up deciding on semiconductor stuff. To the dismay of my mom, who reminds me every day that I could have been a doctor. But thank you, Alon. I really, really loved your mentorship. And then Professor Lang, actually, I took my first E class with you, which was 6002. I don't know what it's called now, but it's the intro circuits class. I really enjoyed it on my first experience in labs. I will forever remember it because it's the only B I've gotten in E at MIT. So thank you. But I love it. I want to take some time to acknowledge all the Velocios group members, past and present. It's been a pleasure working with you guys. It's really the people that make this stuff fun and enjoyable, and you guys have been wonderful. I want to especially call out my mentors in my first few years, Josh and Aman, who really helped me with all the fab stuff, but I had no idea what was going on. And then also Chingyun, who helped me with a lot of lateral stuff in the last 2 years. All right, I want to thank our collaborators, some of them who are on the call, specifically folks over at Rice University, Professor Zhao and Shusong, who took the Indian movement measurements, I think on Saturday for this talk. So thank you very much. I'm really grateful that I spent 2 weeks, I think 2 years ago, in Texas over there doing measurements. And I think out of those measurements, it's been the most productive 2 weeks of my life. I think we've gotten like 3 papers out of it or something. The OSU folks, Ifad and John, for all the regrown contacts. None of this work would have been possible with that. We got those. Savannah and Professor Dusky for all the help with the Venus stuff, as well as the folks that were at NASA and Gary Hunter and his team that organized it. The Lockheed Martin folks who have been funding some of this work and have been just a really good bouncing board for ideas. The TM Expert tool over at PTI, and also the folks over at Bullet, Debbie, Rafi, and Bijoy for all the help with the data analysis and paper publications. All right, I want to take a minute to thank all the amazing MIT staff. None of this is possible without you guys. There have been so many times I've called people at times I shouldn't have, but you guys still pick up, which is amazing. And I'm sorry, but I'll continue to do it, but thank you so much. All the MTL staff, specifically Mike and Bill with all the computer stuff, Joe and Prita who have been wonderful. all the people at the ECS grad office, and also all the undergrads I've had the pleasure of working with, especially over the last year or two, namely Matthew, Denise, Rachel, and you, who have those. Who have been really vital in a lot of the results I showed you today. I want to time for me to finish up soon. Let's see. Oh. Okay, I will do this verbally. I had a lot of fun photos to embarrass everyone, but yeah, I want to thank my parents, my wonderful parents who have shown me support over the years. They're here in the audience. They flew here from California. Yeah, your love has been what has allowed me to succeed so much in the stuff I do. I want to thank my girlfriend, Sori, for the last 2 years. It's been wonderful. She doesn't like public attention, but I'll just embarrass her a little bit here. Yeah, it's been a wonderful experience getting to know you better. And I really enjoy spending time with you. It makes me not want to do lab work, which is great. I'm much more happier now. I want to thank all my friends. I wish I had this picture here. All my friends and family over the years, high school, middle school, undergrad, MIT. Yeah, just really enjoyed your help and everything. I want to take a second to thank all the folks over at Christian Fellowship and Christian, which is kind of MIT's Christian Club, for all the help with faith and understanding God better over the years as well. And thank God as well. All right. And that will end with a thank you slide and some questions, which you can't see. So yeah, thank you so much, everyone, for coming.
Thank you, John, for a really excellent presentation. We have a few minutes for questions, comments. Who wants to get started?
Really great presentation. I did notice for some of your like high temperature HEMTs, after you had measured them, you show like a shift in the threshold voltage, but it actually looks like the devices got better.
Yeah.
After doing it. Why would that happen? Like the threshold voltage shifted, but also the gate leakage dropped a lot.
Yeah.
The sub-threshold slope and everything.
That's a great question. For the nickel ones, I think it's relatively well understood. There's this phenomenon of gate sinking. When you burn in the device, this gate sinks a little bit. And you can basically get equivalently a thinner algan there, and you can have better gate control. For the radiant devices, I'm not sure. That doesn't seem to be what's happening. It could be that the adhesion of the gate to the surface is better, and that might help to some extent. It could also be that the radium has slightly oxidized, in which case it became radium oxide, which is still a conductive metal, but the Schottky barrier height of radium oxide is very high, it's like 60. And that would maybe explain some of the negative threshold voltage shifts you see. That's what we still have to understand.
No questions?
Can I ask a question?
Okay, final question for John.
Hey, people from the room?
No, no.
Any questions here?
Great work, John. I have a question about verification. So which step, it's entirely a very amazing verification result. It's very complicated as a show. Um, so which step is the most, difficult one, Yeah, the gate edge is definitely the most challenging because, you have the edge stop layer, which is good. But you don't really know the etch rate because you get this aspect ratio dependent etching. Because the stem is really high and the hole is very narrow. So the etch rate of the flat sample that you use to monitor is not the same as what goes through that hole. You just kind of have to try or over etch significantly. You have to just optimize it, look at the fit and do that a few times. So that's probably the most challenging part to get right. It's painful, yeah, but it works.
Thank you. Next, please, John again. This concludes the open house session for the next meeting. I would like to close the open. And we're done. Thank you.
Did you stop already? Okay.
Thank you. Yeah.
Yeah, we can.